Hey guys, well this is homework 10 for number 5D. Now you guys in class probably should have done A, B, and C, all of which dealt mostly with momentum. Actually, no, I'm sorry, that's not true. B and C dealt with kinetic energy before and after this event here. But this event we're talking about is a bullet right here coming in, striking a block. And of course we have the collision right here. And then afterwards, the bullet gets lodged in the block and that whole system moves some distance. It slides across that tabletop or whatever surface it was on. And that's indicated by delta x. And that's what we're trying to find with part D right here. Part D asks us, what is delta x such that that block comes to a stop? So really, if we think about this, we need to say once this bullet block system right here is in motion. Once this is in motion, what is the only force bringing it to a stop? And if you think about it, take a pair of keys or a pencil or your iPhone, whatever, slide it across the desktop. Why does it come to a stop? Because of friction. So friction is going to be the force, and in fact the only force acting on this. So the net force acting on this block and bullet system is going to be friction, what we would call static friction. That's the only thing bringing it to a stop. Once this is in motion, friction is going to be acting in the opposite direction. So the net force, or the only force, is kinetic friction. Let's find out how to calculate that. Well, if you remember from our friction chapter, that to find friction, that would be the coefficient of friction, which is that unitless number that is a measure of how rough the surface is, times, you could say, the normal force, but I'm going to say mass times gravity, which is basically the same thing. But I actually really should be careful here because, let's erase that there. Mass of what? In fact, I'm going to change my eraser here a second. There we go. Mass of what? Well, that should be the mass of the whole system. That's the mass of the, we have a bullet and a wooden block, so I'm going to put B and W. Mass of the bullet and wooden block system times gravity. That's going to be very important later on. Okay, so that's the net force acting on this system. And if you recall from our problems several chapters ago where we dealt with net force, if we can state that kinetic friction is the net force, we can also state that the net force, or we can also state the net force a different way. It's always true, and if you recall, we always drew these arrows right here saying that it's the same thing. Net force is kinetic friction, but it's also true that the net force is is mass times acceleration. Or in this case, it's going to be a deceleration, because this net force of kinetic friction is going to be decelerating this block to a stop. So, again, this mass, what mass is this? Well, this mass is the bullet and wood combination right there. So why don't we set these equal to each other, since they are both equal to net force, and we can solve for the acceleration or the deceleration of this. You may be asking yourselves, well, why? Why do we care about the acceleration? Because we want to find this distance, delta x right here. If we find acceleration, we know the initial velocity, that is after the collision, and we know the final velocity has to be 0. And so we can easily solve for delta x if we first solve for our acceleration. So let's set these two equal to each other. Our kinetic friction equals mass of the two objects together times A. We can really say that mu k times mass of the bullet and wood combination times gravity equals mass of the bullet wood combination times whatever acceleration it's experiencing. And we can see right now that these two are going to go away. So our acceleration is going to be simply nothing more than our coefficient of friction times the acceleration of gravity. And our coefficient of friction, of kinetic friction, is 0.45 times 9.81 meters per second squared. And that gives us an acceleration of, where do I have it here? Oh, I just lost it. 4.41. 4.41 meters per second squared. Or really, it's a deceleration. It's a deceleration because that force is acting in the opposite direction. Okay, so 4.41 is our deceleration. So that should make finding x fairly easy now. Our delta x, if you recall, we have an equation much like this, that v final squared equals v initial squared plus 2 times the acceleration times delta x. And when we solve for delta x, we can say that, let's subtract this negative vi squared on both sides. So v final squared minus v initial squared. And then let's divide by 2a right here, which will leave us with delta x divided by 2 times acceleration, which we just found right here, equals our displacement. So what's our v final? Well, up here, we said our v final after this comes to a stop is 0. And our v initial is going to be very important. What is that? That's what we found. That was our answer for part A. That is the velocity of this bullet and block combination right after the collision. So that's the answer for part A, which should be 12.3 meters per second. I probably shouldn't have boxed that. But that's our initial velocity after the collision. So that's going to be 0 squared, if you want to put that, minus 12.3 meters per second, that quantity squared, divided by 2 times our acceleration, which is 4.41 meters per second squared. And that will give us our distance delta x, which should be 17.2 meters. And that's it. For this whole problem, we initially used momentum up here, and then we turned it into a force problem dealing with friction, and then we turned it into a kinematics problem dealing with velocity and distance, displacement and acceleration. So there we go. There's our delta x, and you should get 17.2 for your answer. There you have it. That's number 5D, and hopefully you took a look at it and saw number 4B, I believe, and hopefully these make sense. I'd like you to come tomorrow with questions if you have any, and we'll go over these then. Thanks for watching. I'll see you next time.